Hi guys, good morning, afternoon, whenever you are watching this. Unfortunately, I think that the video is not going to match my voice for this whole thing because I just recorded a whole one for chemistry and it's slow. So thank you, internet. So anyway, you'll hear me. My voice probably just doesn't match with the video. So just a kind of like a touch base with you guys. So since these are for mostly virtual students, I'm just going to talk to you guys for a second. Please make sure that you're going through on the assignments and you're looking at comments that I've left. So I know that it's more difficult to ask for help and reach out being virtual, and you guys are more like self-paced a little bit. So please reach out if you're having trouble. Okay. So I don't always know until I'm grading things, and by then we're kind of moving on to the next thing. So please look out for those comments on graded assignments. If you've done something really well, I've left you a comment. If you're struggling on like a large chunk of things and just really not getting it, I've left an explanation. So please just be checking that. As far as the homework goes, I typically will give you full points as long as it is completed. It's done on time. You have all the units. It's in complete sentences, whatever's asked for, because I really want your homework, to be practice. That's what it's for. I don't want to grade you harshly on it because it's the first time you're trying it, but I am looking at it and making sure that you're doing it correctly. So please double check that. Just if you see a 5 out of 5 or a 10 out of 10, don't assume that it's all correct. Please go back and look at those comments. So today we're going to talk about position in time graphs, so position versus time graphs. So I know that in math classes you guys have looked at graphs. You've looked at different patterns of graphs. I'm sure by now that you've done that in a lot of different math classes, and that's really useful in physics. So the pattern of a graph, the direction that your lines are moving, is going to give you a lot of information. So let's see here. So when you guys are looking at that, this is important here. So for all position and time graphs, no matter how the question reads or the situation, time is going to be on your independent variable, so your horizontal or your x-axis, and then position is always going to be your dependent variable on the y-axis. Okay, so position is always up and down, time is always lengthwise. Okay, so really they're not hard to analyze. The only things you really need to know is how to find the slope of a graph, basically, which I'm sure you guys know. Okay, so if you guys are looking at this here, let me just like move my face. This is, if you guys haven't noticed, I'm a little awkward. That's okay. Okay. So I cannot like move myself out of the way. All right. Third tries the charm. Okay, so if you look at this graph here, you've got a person walking to school. Okay, so we're going to use this graph for the next couple examples. So you have time along the bottom. So this is your independent variable is your time, and then your position is your dependent variable. Okay, so as we move across, you can see that the time goes to 60 seconds and the position goes to 80 meters south is the direction they're moving in. So where does the student start walking from? Okay, so we're looking at this. Where's his position? His position is at 0. Okay, so he's starting where he's at. Where is he walking to? Well, this graph only goes to 80. So for as far as we are concerned, he stops at 80. And since these are positions, they're going to be meters and then have the direction. So let's see. Okay, so home, he's starting at home. So his position, which is your lowercase d with the little vector hat, because it does have a direction, is 0 meters. And when we have 0 meters, we don't need a direction because you obviously haven't gone anywhere. Where is he walking to? He's going to school. Okay, so he's going to school. That distance or that position change was going to be 80 meters south. Okay, so he has moved from his home. He's walked 80 meters south. And then how far is the student's home from the school? The distance is 80 meters. Okay, so you have 80 meters south on there because it gives you the directions, but that's also his position. So his position is 80 meters south. The distance he covered was 80 meters, and his displacement was 80 meters south. So how long does it take for him to walk to school? That's easy. We have a whole graph telling us. So it takes him 60 seconds to walk to school. He must live very close to school. So 60 seconds. How far has he walked after 30 seconds? So just basic graph reading stuff. Okay, so you have 30 seconds down here. You go up till you hit the graph. He's moved 40 meters. Okay, so he's moved 40 meters south in 30 seconds. And then how long did it take for him to walk 20 meters? So again, just reading your graph from a different angle. So we have 20 meters. We go out until we meet the line, go down. You got 15 seconds. Okay, it's pretty simple. You guys should know how to do that stuff. So then we're going to find the slope of the graph. So slope is very easy. It's just rise over run. And I'm sure you've done this so many times. It's probably sickening. But rise over run is a really good way to find the instantaneous velocity on a position time graph. So here, let's just say we're going to do it for the end. So let's say he has walked 80 meters in 60 seconds. So what's the slope of this graph? So the slope is going to be 80 divided by 60, because this is your rise over your run, and you're going to end up with 1.3. And notice the units, okay? So you have meters per second. Okay, so if you have 1.3 meters per second south, we know that meters per second is our unit for velocity. So meters per second south is telling you an instantaneous speed. So since velocity is a vector, it does have to have south at the end because it's indicating a direction that you're moving. But that's all this is. So position versus time graphs are very useful. They give you a lot of information about your time, your position, your velocity. Okay, so that's what we just talked about, what information it gives us. So just make sure that you're understanding that. And like if you saw it written out, you would know that this little highlighted portion here. So the slope of a position and time graph is going to give you your velocity. Okay, so next time we'll start talking about velocity time graphs, and that's going to give you different information, and they have different patterns, and we'll compare all that. But just know for position time graphs, that it's just going to give you your velocity. Okay, so again, we let's see, with your math classes, you guys did rise over run. You use this formula in math, probably like y2 minus y1 over x2 minus x1. It's the same thing for physics. You're just using different variables to describe that information. So you're going to have your distance 2 minus your distance 1, so your position, okay, because it has a little vector hat. So your second, your final position minus your initial position over your final time minus your initial time. So very plainly put, it's just your change in position divided by your change in time. Okay. Let's see. So for the next couple examples, you're going to be looking at 3 different people, 3 kids that are walking home from school. They're all walking 300 meters east, or they're walking to school, I guess. So we're walking to school. This is Alfie. Okay, so Alfie walked 300 meters in 240 seconds. So his average velocity is going to be 1.25 meters per second east, because we're looking at the overall thing. Since this is a straight line, it's a linear graph. This shows that you have the same amount of velocity throughout. Anywhere you anywhere you measure your slope from on this is going to give you your average velocity. And in this case, your average velocity should be the same as your instantaneous velocity. So when you have straight line, average and instantaneous will be equal. So here we have Alfie. He's going 1.2 meters per second. Beth, okay, notice the steepness of this line. She is going 300 meters in 120 seconds. So her average velocity is twice as much as Alfie's. So she's going 2.5 meters per second east. And then Cameron down here. So Cameron is going 300 meters in 180 seconds. So he kind of falls in between. So his velocity is going to be 1.6 meters east. Okay, so hopefully you noticed and you're paying attention to those, the steepness of those lines. So on a position time graph with a linear scale, the steeper your slope indicates a faster velocity. So if you're just looking at graphs, and a lot of times we'll just look at graphs, and you have to understand the pattern for it. So if you have a graph that's pretty consistent this way, and then you are comparing it to something else that looks like this. You've got, get my face out of the way. So you've got not a very steep or even less steep, and then you go higher. Okay, so the steeper that slope is, the faster that velocity was. Okay, so position time graphs can also describe motion over a time period, and it can indicate stopping and speeding up and turning around. There's a lot of things these graphs can tell you. So if you're looking at this position of this student, he's walking to school, okay? So you can tell that from 0 to 15, actually, what is that, 25? Let's see, whoops. So for this portion of time, he is walking at a steady pace, okay? So a steady pace, that's where he started out at. And then for this time period here, he stopped walking. He just is standing still. And you know that because the time is continuing, but his position is not changing. So when the position is not changing, you're obviously not moving. So he's walking at a steady speed. He decides to stop for a minute, and then he speeds up really fast. His slope has increased here. He's running. And then he slows back down back to his original pace. Okay, so during what interval is he moving the fastest? It'd be between these two times, and that's because it's the steepest slope. All right, so if you're going to look at his average velocity for just this little time interval, you're going to use your average velocity formula here. So you're going to have your change in position divided by your change in time. So here we have our change in position was from 40 to 50 meters, so final position minus the initial position. And then the final time for that frame was 37.5 seconds minus 33.75 seconds. Go ahead and just plug that in, do your math. Oops, I need to stop touching it so you can see. So your average velocity for that snippet of time is 2.6 meters per second west. Okay, so what is the meaning of the horizontal line? So we already talked about that. It means he stopped. So if you actually try to prove that by calculating the slope, you're going to get 0. Okay, so since your slope is an indication of your velocity, if you have 0, obviously means you're not moving. So how would this student's average velocity compare to the first student's average velocity? Okay, so both students are going to be walking the same distance in 60 seconds, so 80 meters in 60 seconds. So your magnitudes are the same, even though obviously the first kid stopped and started and ran, and he didn't have a consistent velocity throughout, and your directions would have been different in those two cases. But when you actually compare them, they had the same average velocity. Okay, so if you remember from the first slide with the kid that started and then he stopped and then he ran and then he continued, his average velocity was 1.3 meters per second west, or I think he was going south. But anyway, it's the same average velocity. Okay, so even though the graphs look different, you can still have the same average velocity because averages are considering a lot of data points. So if we're looking at this kind of graph, this also gives us a lot of information. So obviously our position is here, time is on the bottom. You can see that this person started off moving at a constant pace, and then once they made it to 25 meters, they stopped walking. They just stood there, and then they decided to keep going at another average pace. And then they got to 50 meters and they stopped walking. So they stood there for 5 seconds, and then they started again at a little average pace, and then they took a short break, and then this line goes down. Okay, so he's going down. His position is going back to 0. And we know that the position is talking about where you are at relative to your reference point. So if we started at 0, and 0 is our reference point, and our line goes all the way back down to 0 for position, that means we turned around and went back to our starting point. Okay, so the motion of this runner is that he runs, he stops, he runs, he stops, he runs, he stops, and then he turns around and runs back home. Okay, so we know that the horizontal lines he's stopping. The average velocity of the runner in the last section, what does that sign mean? So if you found the average velocity here, let's see if it shows you. Okay, so your final position would be 0 meters, and your initial position was 75 meters because you were way up here and you're going back to 0. Final time was 40 seconds, initial time was 27.5. this gives you a negative number. Okay, so the negative is indicating a change in your position or a change in your direction. So if in this case your, let's see, yeah, it's the negative. So he was going north originally. That's what I couldn't remember. It's right there. Okay, so he originally was going north. North was his original position or direction, I should say. And then when you do your average velocity for this portion of the line and it gives you a negative number, it means that he's switched his direction. So you have two indications of change in direction there. The line has changed, so the direction, the slope of the line has changed, angle, and then you also get a negative velocity. So anytime you get negatives, just be aware that that's indicating a change in your direction. Okay, so his final position and overall displacement would be 0 because he ended up where he began. Okay, so just some reminders here. We know that our average velocity is always going to be the final position minus the initial position over the final time minus the initial time. So just your change in position over your change in time. And then the slope of your graph is going to give you your velocity at that point. Let's see. So we just talked about this. So we have positive and negatives. So here we have just a consistent like flat line here. So if you have 0 for your slope, that means your velocity was 0. So position is not changing over time. So position will be over here. If you have a line with a positive slope, okay, and constant. So if we have a straight line here, it's not curved. Just remember that the steeper this slope is, the faster that object is moving. And then if you have a negative slope, so your line is starting at a higher position and coming back down, that means you're changing directions, okay? So it doesn't mean that you are going slower. It just means that you're turning around. You're going opposite direction. All right, so the last thing to talk about here is going to be the position time graphs of accelerating objects. So these would be graphs that are not linear, okay? So they're going to be curved lines. If you have an increase in acceleration, so say you're driving down the highway and I'm driving 30 miles per hour and then the speed limit changes to 60. So I'm speeding up, right? I'm going to press the gas. I'm going to continue speeding up until I reach the next speed of 60 or higher. So when you get that, you're going to have a curve. So it's quadratic. So you guys talked about quadratic functions and parabolas in your math classes, and we are going to analyze them for physics. So you can also get your instantaneous velocities from this as well. Okay, so we know that in this plane, he's obviously not moving at a constant velocity because you have a curve here. Okay, so no straight lines. It does move at constant acceleration though. Okay, so the more time passes, the higher and higher and higher it gets. Okay, so we're moving with a constant acceleration. So constant velocity means you're keeping the same speed the whole time, and the constant acceleration means that you're increasing your speed the whole time. You're speeding up until the end of the graph. All right, so if we're going to look at this, you can tell that at 2 seconds, we are at 10 meters, and then 4 seconds, we're at 40 meters, and then 90 meters, then 160. So just the numbers themselves are showing you some acceleration there. Okay, so with the curves on the graph, you can't immediately just find the slope anywhere because you have a curve. So what we're gonna have to do is draw some tangent lines and then calculate the slope to find your instantaneous velocity. Okay, so what you guys are gonna do, and I'll show this on a graph, you're gonna locate the position of that object at the time that you wanna find the instantaneous velocity for. You'll use a ruler or like draw a line using your iPads that touches the curve but doesn't cross the curve. Okay, so if you have, I can't bend. Okay, so I'm in the video there because I got interrupted. So let's start over here. So we were talking about tangent lines. Okay, and that's what these red lines are. And you can see these little blue X's. Okay, so let's just look at this first one. That's the example over here. We drew our tangent line. So the tangent line, we're looking at 2 seconds is what this question is asking. So determine the instantaneous velocity at t time equals 2 seconds. That means that my tangent line needs to touch my curved line right at 2 seconds, and then it should extend in either direction as far as you want. So if you want to draw this line all the way out to the edge of the graph, that's fine, or you can just stop it here like they have. So for the instantaneous velocity, you're using values somewhere else on that line, on the tangent line, to determine like the final and initial position. So if you have a tangent line here, it's touching your line right where at 2 seconds. You have either end of this to create your little triangle, right? So this line we extended all the way up until it hit 20 because that's a good stopping point. We can read that number easily on the graph. And then we extended it back down to position 0 here because that's another easy spot for us to read on the graph. So these would be your final times in positions, and then down here would be your initial times in positions. So that's what you're plugging in. So you draw your little tangent line, you extend it as far as you would like, you take a point at one end and a point at the other end and plug that in to your instantaneous velocity formula. So here we swipe it up here. So this line extends up here, which is where we decided to stop it at position of 20. So our final position was 20 meters. Our initial position, if we go back down to the other end, is 0. And that's what we have here. So final position was 20, initial position was 0. And that's divided by your final time minus your initial time. So here again, we go down. The final time was 3 seconds at the end of this line. Okay, so wherever you mark it at, so I marked it at 20 meters, there is where you need to go down and measure the time from. So we go down here, the final time was 3 seconds, and then the initial time was 1 second. Sorry, there's like people outside my classroom. I can see them out there. So we'll do a couple more examples, but that's how we're getting this division. So if you have 20 minus 0 is 20, and then 3 minus 1 is 2. So you're gonna have 20 divided by 2 and gives you 10 meters per second west. So the instantaneous velocity right here where it's touching the tangent line would be 10 meters per second west. So some more examples of that. Here at 4 seconds. So if you look here, at 4 seconds, we went up and we're going to draw a little tangent line. So we drew the line, we extended it down here to where it hit like a crosshair, where it's an easy measurement. We extended it up to where it hit another crosshair, where it's an easy measurement. And we're going to find our final and initial positions. So here our final position is going to be 60 meters, and our initial position was going to be 20 meters. So if you look here, your final position was 60 and your initial position was 20. And then same thing. So here, this is the position we're taking at. So what was the time? The time was 5 seconds. So the final position was here. So the final time is 5 seconds, and the initial position was here. So the initial time was 3 seconds. So we're plugging that back in. So you have your final position at the end of that tangent line minus the initial position at the beginning of your tangent line divided by the final time and minus the initial time. So you end up with 40 divided by 2, which gives you 20 meters per second. So at 4 seconds, right here where it's touching our tangent line, that instantaneous speed is 20 meters per second. Okay, so we went from 10 meters per second to 20 meters per second in that time frame. And then again, last example here. So at time of 6 seconds. 6 seconds, we go up, we draw our little tangent line. It extends as far or as little as you want. We stopped it here because it's right at a crosshairs and it's easy to measure from. But you can draw these lines all the way across if you want to, as long as they don't cross over your parabola. So here at 6 seconds, we drew a tangent line. I stopped it up here when it hit the position of 120 and the time of 7 seconds. And then down here, we stopped it at 60 meters and 5 seconds. So your final position is 120 minus your initial position of 60 over your final time of 7 seconds minus your initial time of 5 seconds. So that fits here. So 120 minus 60, so final position minus initial position over the final time minus the initial time. So now we have an instantaneous velocity at 6 seconds of 30 meters per second west. Okay, so you can see how that increased exponentially. So you had 10 meters per second west, 20 meters per second west, 30 meters per second west. So you're increasing your speed as you move along, so your acceleration. So tangent lines, once you get those down, those are honestly the easiest way to do instantaneous velocity on an acceleration position time graph. But if you are familiar with calculus and you would rather do it this way, if you know your position function, you can use the derivative and find it, your times and your velocities from there. So if that's what you prefer, then you go for it. But this is the way that I teach it. So if you have questions, this is the way that I'm going to be able to address it for you. So just again, with these tangent lines, you are drawing a line, just the centers, touching it right where the time that was asked to determine the instantaneous velocity at. And then you are basically picking a spot on either end of those tangent lines to use as your final and initial positions. So that's it for today. It was probably a lot. It would probably be a good idea to go back through the slides and just read through them again. You guys do have a gizmo to complete and an assignment. So you have two things to do. So the gizmo is taking you through basic position time graphs and just kind of looking at trends and the way increasing or decreasing speeds and stopping and turning around changes the way the graph looks. And then the assignment is going to be this stuff. It's going to be position time graphs of accelerating objects. So please give it a look over. Let me know if you need any help, and see you next time.